Okay, so hi everyone, I'm Chen from MIT, and I'm here to talk about on the impossibility of SNARGs with short CRS or revising Gentry-Wichs barrier in the non-adaptive setting. So this is a joint work with Chen from Northeastern University. To begin with, let's recap the definition of SNARGs, succinct non-interactive arguments, which is a proof system where we have two parties. One is the prover and the other is the verifier. So the prover wants to convince the verifier that some statement is true, represented as the instance X is in some NP language L. So during the execution of this protocol, both prover and the verifier have access to some common reference string, which is honestly generated, and then the prover it uses the corresponding witness for the instance X and computes a short proof from it, and then sends the proof to the verifier, and the verifier performs the check by reading the instance, CRS, and also the proof. And it is also guarantees that the length of the proof is significantly shorter than the length of the witness. So SNARG guarantees that if the instance is in the language, then the honestly generated proof should be accepted. But otherwise, no polytime adversary can provide an accepting proof for a false statement. And what's more, for this soundness property, actually we can define it by two ways. One way that we call it adaptive soundness, which is we first give the adversary the CRS, and then we allow it to choose the instance it wants to prove as well as the malicious proof. So in this case, the adversary has like the flexibility of first seeing the CRS and then choosing the instance it wants to prove. So we call it adaptive soundness. And then there is also non-adaptive soundness, which says that we require the malicious prover to further choose the instance it wants to prove, and then we give it the CRS, and then it provides the malicious proof pi. So it's called non-adaptive soundness. Okay, so SNARG is a wonderful primitive. Then the question that we care about is how can we construct SNARGs? How can we build SNARGs for NP? So there's a lot of work, a huge number of brilliant ideas like on this problem, but unfortunately for many of these works, they can only construct SNARGs for NP in the random oracle model or from knowledge type assumptions. So why is this the case? And actually, this phenomenon was already addressed in the seminal work by Gentry-Wichs by their Gentry-Wichs barrier. So they saw that there is a barrier for adaptive SNARGs. If the SNARG for NP has a black box reduction from falsifiable assumptions, then the reduction time cannot be polynomial. Okay, and here let me explain what it means by black box reduction from falsifiable assumptions. So it is that there is some efficient reduction algorithm which interacts with the malicious prover. And then finally at the end of the interaction, the reduction algorithm outputs one bit indicating that whether or not you can use this malicious prover as a black box to break the underlying cryptographic assumption. Okay, but it has already been 14.5 years after the publication of Gentry-Wichs, which was published in Stock 2011. And nowadays, actually, we do know how to construct SNARGs for NP from well-founded assumptions. So for non-adaptive SNARGs, we know how to construct them from indistinguishability of obfuscation or from witness encryption with a PV proof of correctness. And also for adaptive SNARGs, we know how to construct them from sub-exponential security of indistinguishability of obfuscation. But however, all of these techniques, they sort of overcome the Gentry-Wichs barrier by using some exponential time reduction, which likely necessitates long CRS. But long CRS is not very practical for SNARGs, since CRS should be generated by some honest party, and if the CRS is long, then this SNARG is not so useful in real-world application. And also, on the other hand, we know that for adaptive SNARGs, as shown by Gentry-Wichs, it is legitimate to use sub-exponential time reduction, but in the non-adaptive case, actually we don't know whether this sub-exponential time reduction is necessary. So the question that we want to answer is, do we need sub-exponential time reduction in the non-adaptive setting? Or more particularly, can we extend Gentry-Wichs to the non-adaptive SNARGs with short CRS? Okay, and then towards answering this question, let me first introduce the brief idea about how Gentry-Wichs works. So let's look at this interaction between the reduction algorithm and also the malicious prover. So in this interaction, the reduction algorithm first sends some CRS to the malicious prover, and the malicious prover answers some instance X and also a SNARG proof pi. So here, the crucial observation is, if this instance is not in the language, then by definition of security reduction, the reduction algorithm should break the cryptographic assumption. But otherwise, if this instance is in the language, then this reduction algorithm shouldn't break the assumption, since otherwise we can set the prover to be the honest prover that just proves some yes instance and that just proves some yes instance. So as a takeaway, this reduction algorithm should learn membership of X from shortcut pi, which, as shown by Gentry-Wichs, is impossible. Okay, but that's the adaptive setting. And the first challenge that we need to answer in the non-adaptive setting is that the reduction algorithm can perform some sort of rewinding. So on the right, we have the interaction between the malicious prover and the reduction algorithm in the adaptive setting. And then on the left, in the non-adaptive setting, things gets a little bit trickier. Since in this case, the malicious prover needs to further choose the instance it wants to prove, and then after that, the reduction algorithm can issue many CRS queries to the malicious prover. So it can first send CRS1, getting the corresponding proof pi 1, and then sends the next CRS, getting the corresponding proof, and so on. So in total, the reduction algorithm can send a polynomially number of different CRS to the malicious prover and getting the corresponding SNARG proofs. So in order to extend Gentry-Wichs to the non-adaptive setting, the first question that we need to answer is, can we find an NP language such that deciding membership of X is hard even if you can rewind the prover? So for this question, we give our first result, which is a barrier for short CRS non-adaptive updatable SNARGs. So for updatable SNARGs, I will explain what it is later. For updatable SNARGs with a poly-lambda size CRS, it is impossible to prove non-adaptive soundness via efficient black box reduction from falsifiable assumptions. Okay, then what is updatable SNARGs, which is also known as incrementally verifiable computation for NP? So this is sort of SNARGs that we consider the statement is it proves is you apply some non-deterministic function f n times to some initial state z0, and you result in the final state Zn. So the application is the following. The first, in the beginning, you have some state z0, and then you read some non-deterministic witness w0, apply this function, and you get the next state z1, and then you read the next witness w1, and then you get the next state z2, and so on. So for updatable SNARGs, it supposed that you can incrementally update proof of I applications to a proof of I+1 applications. So this means starting from the proof pi 0 for the first step of computation, you can compute from pi 0 and the intermediate state z1 and the witness w1, and then only from then you can compute the next proof pi 1 for transiting z0 to z2, and so on. You can compute pi 2 by reading w2, and so on. So the crucial part is that during the computation of the proofs, you can forget earlier witnesses. You only need like W0 to like compute pi 1, W0 to compute pi 0, W1 to compute pi 1, and so on. So this is the special property of updatable SNARGs. Okay, and then this is like rewinding the prover, but actually there is an additional challenge, which was introduced, which is a new reduction technique introduced in a recent paper that we call it non-uniform reduction, which is as following. So let's look at this like overly simplified interaction between the reduction algorithm and also the malicious prover. Since in the non-adaptive setting, the malicious prover needs to further choose the instance it wants to prove, so we can actually fix the random coins it uses and therefore fix this instance it wants to prove. And therefore, we can non-uniformly provide the reduction algorithm some auxiliary information that can arbitrarily depend on the instance. So that is, in this non-uniform reduction, we have this auxiliary information z, which can be any function about the instance, where this function may not be efficiently computable. And so, like, for this non-uniform reduction, a natural question to ask is, can we extend Gentry-Wichs to non-uniform reductions? Can this non-uniform reduction be useful to bypass Gentry-Wichs as an alternative, a different technique other than some exponential time reduction? Okay, so it shows that actually it cannot unless you develop some very new, very different techniques. So there's a barrier for short CRS non-adaptive SNARGs with non-uniform reduction. We show that for SNARGs with polylambda size CRS, it is impossible to prove non-adaptive soundness via efficient black box non-uniform reduction, but with a constant number of queries to the malicious prover from falsifiable assumptions. So here, let me explain this restriction of you can only have a constant number of queries. Actually, all non-proof techniques for non-adaptive SNARGs, including those from indistinguishability of obfuscation or those from batch arguments, all of this security reduction actually can be made one query. So this means even if you can use non-uniform reduction to bypass Gentry-Wichs, completely different reduction techniques that essentially utilize many queries to the malicious prover is necessary. Okay, and then let me give some taste about the techniques that we use to prove this result. So the key tool that we use is super bits generator, which was introduced by Rudish in 1997. So this is just the variant of PRG, but it's a PRG against a non-deterministic computation. So the definition is the following. For any non-deterministic adversary A, the probability of A accepting a random string should not be significantly higher than the probability of A accepting a random PRG or a random super bits generator image. Here, I comment that it is crucial that there's no absolute value on the left side of the inequality, since otherwise it is actually trivial for the adversary to accept a random PRG image with probability 1, since it can just track if it has a pre-image. But on the other hand, we don't know any good way for the non-deterministic adversary to accept a random string with higher probability. Okay, so for this super bits generator, we prove an unbounded liquid simulation theorem. So we saw that for any augmented distribution of random string, that is, we have an auxiliary information, poly-size auxiliary information about the random string, there exists an augmented distribution of random PRG image such that these two distributions, even in the presence of the auxiliary information, are computationally indistinguishable. So probably for normal PRG, assuming some exponential time hardness, we can only have liquid simulation for length-bounded auxiliary information. That is for the length of the auxiliary information should be bounded by n to the power of 0.1, but here we have unbounded leakage simulation for adding poly-size auxiliary information. And actually, what's more, this result can apply to any distribution pairs that are indistinguishable against a non-deterministic adversary. So I believe this is like sort of like an interesting contribution of its of its own interest. And also, like, for this unbounded leakage simulation, the takeaway is that for this language of superbit generated image, actually the auxiliary information is not so useful for us to tell whether like the instance is a PRG image or not. So it's useful for proving our barrier. Okay, so finally, let me summarize all this work and ask something about the future works. So in this work, we try to answer two questions. The first one is, can we extend Gentry-Wichs to non-adaptive short CRS SNARGs? And second one is, can we adapt Gentry-Wichs to account for the recent non-uniform reduction technique? So for the first question, we show that yes, for updatable SNARGs. And for the second question, we show that even if you can bypass Gentry-Wichs using this non-uniform reduction technique, essentially new techniques are necessary since you need like essentially many queries in the security reduction to the malicious prover. And about the future works, I think a very interesting direction is, can we go beyond the black box reduction? So currently, I'm guessing that maybe we can do something by using like those interesting works on like meta proof, like those from proof complexity. But for now, I'm not so sure about that. And I'm very interested to hear like any like new progress. Okay, so that's all. Thank you so much for like listening to this talk. Okay.